Um, yeah, so this is a joint work with Ofer Feinerman, Emanuele Natale, and Amos Korman. And I should start by saying that it's a hybrid project because we're not only computer scientists. In fact, Ofer Feinerman is a physicist working with ants, and so he does experiments. And as Anna said in the introduction, in this work we have in mind a setting, an experimental setting with where ants go out of their nest to look for food. But I saved this for the end and start with the theoretical part. So yeah, these are our affiliations. So we're interested in a rumor spreading problem where the agents don't have a fixed graph to communicate, but rather they interact at random. And the interactions, in fact, on top of being random, they are also noisy. So more specifically, the model we work with, the pool model, is defined as follows. We have n agents, and at each time step, two of them are selected uniformly at random, and then they interact. So what this means is, so everybody at all times is displaying a message, and when two agents interact, one of them gets to read the message that the other is holding, except for the fact that there is noise. So maybe the first one is displaying 0, but you read 1. And we don't want to be too specific about the noise model, so we just assume that any message can be transformed into any other message with some probability delta. And of course, the delta will show up in the result in the end. So I said it, the task we consider is rumor spreading. Broadcast is also a valid name for it. So we have a designated agent, the source, that holds a binary information and wishes to spread it to the rest of the population. So we count the number of interactions or time steps that are needed before everybody knows the value of the source. And sometimes I use the word rounds in place of n times n interactions. And yeah, what we want is constant advantage over random guessing. So with the setting clear, I can say what our result is. It's a lower bound, in fact. We show that in this setting, no rumor spreading protocol can be faster than quadratic in terms of rounds. And this is to be contrasted with, like, most protocols in this type of settings are logarithmic. So this is like a very high lower bound. Okay. So just a word comment on the setting. It's a rather liberal setting. Okay, we need noise and random meetings, but apart from that, we can allow for shared randomness. The alphabet size can be big, and the nodes, they have unlimited power. So the lower bound is purely information theoretic in nature. And yeah, before I say a word about the proof, another remark is that we crucially rely on the fact that we work in this pull model, as opposed to the push, which is a close parent. They often go hand in hand, these two models, and maybe they are, in some settings, they are interchangeable, but not here. So what is the push? In the push, if I'm knowledgeable and I have a piece of information to convey, I will actively engage in an interaction. I will pick up the phone and then try to contact someone to spread this information. In the pull, in contrast, if I have something to say, the only thing I can do is display it in my message and then wait until someone contacts me. So it's a big difference. And I mention this because in the push, a protocol is known to work. There is a known protocol that works efficiently. And morally, the idea is that the very fact that you're engaging in a communication is reliable in the push. And so, okay, we had this actually in a talk yesterday with BFS construction in the asynchronous distributed model. It was very much the same thing. And it's also something that is used in the beeping model. So okay, what's the idea of the proof? Basically, in a sentence, we reduce to a coin distinguishing task. So fix an agent and look at what she receives from the rest of the world. So for us now, everything that's on the right of this dashed line is like a closed black box system. And once in a while, the agent on the left gets receives a message. So just to be specific, let's say that the messages are just bits. And so she gets these random bits. And if you think of two settings where everything is the same except for the source, then the only way that the bit that she gets is different is by basically pulling the source. So the difference in the bias of the coins, if you think of it as coins, is just 1 over n. So, okay, the task, what do I mean by coin distinguishing task is the following setting. You have an observer that is presented with a sequence of coin draws. And these coins could either come from some distribution P0 or P1. And the two distributions differ by just this little epsilon in the parameter. And this, we think of it, as I said before, morally as 1 over n. And then the question is, how many samples does it take before the distinguisher knows from which distribution the samples come from? So there is a folklore result that says, essentially, you need delta times epsilon to the -2 samples. And yeah, it's important that we are away from 0 and 1 here, because otherwise, the moment, so if delta was 0, the moment you see a 1, you know that you're dealing with P1. So that's why we need this delta uniform assumption that I mentioned previously. So that's good, but we are in a slightly more complicated setting. We are not observing independent draws. We are observing things that there are lots of dependencies, basically because agents can adapt to what they saw in the past. So maybe I've been seeing only zeros, and then I will decide to display 0 myself, or I mean, you could imagine all kinds of things of this sort. So we need to account for this, and basically, what we need to do is look at the proof of this folklore result and see how to adapt it to this case where the parameters of the variables we're considering vary with time. So let's look at the proof. It goes in a few steps. The first step is to realize that the relevant notion is the total variation distance between the two distributions. That gives you a lower bound, this expression on the best probability of error that you can hope for. Then it turns out that total variation is not super convenient to work with, so it's better to use a Pinsker to replace it by Pinsker inequality to replace it by the KL divergence. And so in a previous talk, this was not enough, but for this folklore result, using this inequality turns out to be enough. And why is it good? Because it tensorizes. So that means that the KL divergence tensorizes. It means it behaves nicely with respect to product distributions. So if you feed it with product distributions, it will nicely split into the t times the KL divergence of the marginals. So then you put everything together, compute the KL divergence of the marginals, and get the lower bound this way. So okay, back to our setting. What do we need to modify? So as I said, now the parameters of the variables we consider, they may evolve with time in an intricate, complicated manner. But okay, we can still write the first two steps as we did before. And things break only at the third step because we no longer have independent draws. So the joint, this stands for, I forgot to say it, but the joint distribution of t draws of the variable under the law P0. So we replace this, we need to do something else here, and we just basically replace it by a chain rule, which I wrote in a stylized, simplified form. But basically, this allows you to condition on the history so far, and then compute the conditional divergence based on what happened so far, what were all the messages that were exchanged so far. And similarly to the previous case, we can still compute what this scale divergence is in this case for the two marginals and conclude as before. So that's it for the proof. Yeah, using this plugging in epsilon equals 1 over n, we get the result we wanted. And on top of it, so I won't go into details, but we can also obtain the result for a few variants. Maybe if everything happens in parallel, the proof still works, basically. Now I was thinking of interactions happening sequentially, but we can deal with parallel. And also, even if you know who the sources are when you meet them, you can still get a lower bound. So it's slightly worse, but it's still something with an extra argument. It's still polynomial. So at last, we can move to biology, as I promised, and talk about the ants and the crickets. So this experimental setting that Ofer had in his lab was as follows. There is a group of desert ants that he raised, and they are placed. So he puts a cricket here in the vicinity of the nest, and then waits until an ant goes out and finds it. And so these ants typically work alone. And when they find, so they're scavengers, and when they find a dead insect, they try to bring it back home. And typically they do it by themselves. But in this case, the insect is too big, so a single ant cannot do it by herself. I actually wonder even if it's not like pinned, so there is no chance that she will be able to move it. But OK, never mind. So she goes back home to try to recruit other ants to help her carry the food item back home. And why is it relevant? Why is this setting relevant to us? So first of all, the interactions, they happen in a somewhat randomized meeting fashion. So they happen somewhat randomly. And this we can check empirically with the data. And then, so as Anna said, the alphabet they use, the language they use to communicate is bumps. They bump into each other. And we can also estimate, given the data, what is the noise in the interactions. And so we see that these two assumptions that we make are met in this setting. The thing that is a little bit more tricky is whether it's a pull or a push. So it would, I guess, be a bit too bold to say that it's purely a pull. It's probably a mix of the two types of interactions. But the idea is that in the obscurity of the nest, they bump into each other by accident. This we know it happens. And they react to these accidental bumps statistically in a similar way to bumps with informed ants who are trying to take them out to fetch the food. So it seems that they are not able to distinguish an interaction that is made by someone that was not wishing to communicate anything from someone that tried to communicate something. So then what's nice is that if we look at how the time of the recruitment process evolves with the group size, we indeed see that it deteriorates when you increase the size of the group. So here are just some figures to back up what I just said. This is the part where we check that the interactions look random. This is the part about estimating the noise in the interactions. In another work, in fact, Ofer also estimated how much information goes into each bump in terms of number of bits. And then, yeah, the time until the recruitment is over. So we declare that the recruitment is over when two other ants leave the nest after the one that actually found the food in the first place. Okay. So that concludes the part about ants. And then I want to And with a slightly more speculative note, so in this setting, maybe I didn't insist, but we view this as a very inefficient rumor spreading process, and this is in accordance with the lower bound that we show to some degree. But what's interesting is that we can also look at cases in nature. Now that we're equipped with this lower bound, we can go out and look at the world, and we can also consider cases where the spreading happens somewhat efficiently. Okay, it remains to be defined what efficiently means, but for instance, we can look at bird flocks, and okay, so it seems it's a very complex system that has been studied both by physicists and by computer scientists, and the idea is that they're able to navigate in, like, maybe one bird detects that there is a predator and will change direction, and this change of direction will propagate to the rest of the group. So we are in a setting where also it seems information is being propagated to the whole group, and this change of direction happens rather fast, in a matter of a few seconds. So we can look at this through the lens of the lower bound and ask, if it's efficient, then what's the assumption that we're making in the lower bound that is not verified here? So it seems the first thing is the interactions between the birds are not random at all. They are local in nature, so the birds will look at, maybe it's what the people in a fixed what their neighbors in a fixed radius are doing. Maybe it's the 3 closest neighbors, but all the models assume some form of locality in the interactions. And it's also been experimentally validated. So that's one thing. And then there is another work that we stumbled upon that argues that when the birds are more aligned, then the response time to an external stimuli is smaller. So they react faster if they are more aligned. And we can try to think about this with our lower bound in mind, and maybe what's hidden there is a noise reduction mechanism. So maybe they are better able to sense what their neighbors are doing when they are all flying in the same direction. So with that, I will conclude. And so the meta statement that we have in this work is that when you have both noise and random meeting pattern, like in this passive model of communication, it's hard to spread information if these two ingredients are put together. And so from an evolutionary standpoint, maybe it makes sense to, if really this information spreading is crucial to the survival of the group, then maybe it makes sense to invest to either get rid of the noise or change the communication setup so you have a fixed graph over which you're interacting. So that's it. Thank you for your attention. Yes. So yes, as far as I know, this is not something that is very much observed with these species in these experiments. So Offer only talks always about pairs of ants interacting.
And the other question is, they have a clock.
The ants?
You said there's a tick of a clock. So what do you mean by that?
Oh, sorry. So what I meant is that you could assume in the lower bound that even if the agents share a clock, then they would still not be able to solve the problem. I'm not saying that the ants have a clock. It's just...
And the third thing is that they are tossing coins.
This I'm not so...
In your algorithm.
Yes, so the algorithm, I haven't said if it's deterministic or randomized. In principle, they could be tossing coins. I'm not sure to what degree the ants' behavior, what they do, is randomized or well described.
But your algorithm, you got this bias, right?
Yeah, so that's in the lower bound. The randomness in the lower bound also stems from the fact that the interactions are random. So that's why you have random coins.
In the video, do they succeed in dragging that dead carcass Or they just give up.
I'm not sure. I think the video stops at least before they manage to drag it. So the story doesn't say.
It's a very sad story.